Thank you for joining this talk. My name is Lima, and I'm going to present our paper, SyCoCa, Symmetrizing Contrastive Captioners with Attentive Masking for Multimodal Alignment. And this work is done in collaboration with researchers from our group. We propose several improvements to push the frontier in multimodal alignment in vision language model research. In recent years, the dramatic process of the multimodal alignment between vision and language has reshaped computer vision research in some sense, and the availability of the large-scale datasets and powerful computational resources has led to many seminal works and impressive results in this field. For example, CLIP uses a contrastive objective, namely the ITC task, to constrain global representation to align to constrain global representation alignment of the entire images and sentences, while SyCoCa integrating a directional image-to-text generation objective, namely an image captioning task, local representation with CLIP, to promote fine-grained multimodal alignment and result in impressive results. However, CoCa only utilizes visual cues to generate textual descriptions, yet disregarding the visual context reconstruction from text cues. Thus, here comes our first motivation, symmetrizing SyCoCa by introducing a text-to-image reconstruction task to further enhance the multimodal alignment. And the second motivation comes from common sense, namely the text description are highly abstract, but the image content are rich. For example, the caption a football match may well imply a vivid scene of a great field, multiple players, and a crowded audience, while the caption of a picture about the family dinner of Thanksgiving Day would really delineate the furniture in the room in details. Therefore, it's necessary to choose appropriate local regions and representations for the alignment. In summary, the main contributions of our work are listed as follows. First, we expand the text-guided mask image modeling, namely TGMIM, to symmetrizing SyCoCa, which improves the understanding between images and text from both global and local perspectives. Second, we employ an attentive masking strategy to select effective image patches for image captioning and TGMIM respectively to promote the bidirectional local interactions. And thirdly, we validate that our proposed SyCoCa outperforms CoCa on several downstream tasks. As shown in the figure, the overall model architecture consists of four key components, namely the image encoder, the text encoder, the text-to-image decoder, and the image-to-text decoder. Here we use a vision transformer as the image encoder, which takes image patches as the input and encodes them into a sequence of embeddings. And we use a causal mask transformer as the text encoder, which takes the simple BPE tokenized input text and converts it into a sequence vector. And the decoders utilize cross-attention transformer modules to deeply fuse image and text information. And the introduction of the training objectives of SyCoCa starts from an image-text pair dataset consisting of pairs of image and text. And the image encoder and text encoders are responsible for encoding the image and text respectively and yielding the embeddings. And reaching the SyCoCa uses three objectives, namely the image text contrasting and the image captioning and the text-guided mask image modeling, where the IC and the TGMIM constructs the image-to-text and text-to-image cross-model interactions and takes the high-attention masked and the low-attention masked image as inputs respectively. And we propose an attentive masking strategy to select the appropriate image patches for IC and TGMM respectively, and to promote the bidirectional local interactions. And specifically, we first use the token-wise maximum similarity between the image and the text embeddings to evaluate the correlation between the image patches and the text words. And then we select image patches to be masked based on the scores. And for TGMM, we masked a fixed radio of the top scoring patches, while for the image captioning, we mask the patches with the lowest scores at a fixed ratio. And to demonstrate the effectiveness of our proposed SyCoCa, we conduct extensive experiments on 5 downstream tasks, where both CoCa and SyCoCa are trained from scratch on CC20M. And SyCoCa outperforms CoCa in all downstream tasks and excels at capturing text-related fine-grained visual elements. Specifically, in zero-shot image text retrieval, SyCoCa consistently outperforms CoCa, showing the gains in the range of 5 to 50% for record 1. And in image captioning, the SyCoCa outperforms CoCa across all metrics and improves by 4 to 6% on MS-CoCo and 1 to 3% on lookups compared to CoCa. And in VQA task, SyCoCa surpasses CoCa in all cases and achieved the remarkable improvements of 8 to 9% on different speeds. And in image classification task, SyCoCa outperforms CoCa in 7 out of 8 cases in zero-shot classification, and all 6 cases in fine-tuned fine-grained classification. And to obtain the intuitive comprehension of the advantages of SyCoCa, we use GrandCam to generate attention location maps. We can observe that SyCoCa can capture fine-grained visual elements related to informative words in the text. And all these results demonstrates the effectiveness of incorporating bidirectional predictions in SyCoCa to enhance the understanding and differentiation of fine-grained elements within the visual representation domain. And in summary, in this paper will introduce a novel vision language pre-training method called SyCoCa, which aims to further enhance the multimodal alignment. And our approach focuses on improving the fine-grained understanding between the vision and the language modalities, and by incorporating the TGMM training objective into the CoCa framework, we establish bidirectional local interactions, which leads to a precise and fine-grained alignment between the vision and language modalities. Additionally, we propose a new attentive masking approach for TGMM and image captioning, which selectively mask image patches that have strong correlations with text caption to enhance the cross-modal interaction and significantly improve the overall performance. And through extensive experiments on 5 vision language tasks, we demonstrate the effectiveness and generalization ability of our SyCoCa. And as a complementary note, we wish to draw your attention to a related project, the M-square encoder, which is an advanced version of the SyCoCa by large-scale training. You can access this project by scanning the QR code. And with that, I conclude my presentation. Thank you for your listening.